All right, let's take a look at another example. So here we want to take a look at find the triple integral over q of 1 taking the derivative dv with respect to volume. So really, this is asking us to find a volume of a solid question. So it says where q is the solid, and it's going to be bounded by x equals 0, y equals 0, z equals 0, and x plus y plus z equals 1. So we've got 4 different planes that we're bounding by. So let's actually draw this region, this surface that we're trying to draw. So x equals 0, well, that is all the points along when x is 0, so that would be like the entire xz, or sorry, the entire yz plane. So we've got, let's see, x, y, and z. We've got y equals 0, which would be the all along when y is 0, we get the xz plane, and when z equals 0, we get the xy plane. So if we think about what that's doing, is it's basically trapping us in this first octant, so where all of the we've got those 3 planes, so we're gonna be trapped in one of the octants. And then to see which one, we can see where does this plane lie. So we can find the intercepts of the plane x plus y plus z equals 1. So if we let, say, 2 variables at a time be 0, we can find those axis intercepts. So like when x and y are both 0, then z will be 1. And when, similarly, say x and z are both 0, then y is going to be 1. And when, like, y and z are both 0, then x is going to be 1. And so what we've got then is then we're going to have this portion of that plane, and then we'll be bounded in the back kind of by this triangular side, on the side by this triangular side, and then on the bottom by the xy plane. So we kind of end up with a pyramid-ish shape. So that's our solid q. So then we need to look for bounds for q. So let's first look for bounds for z. Well, if we take a look at it, we can kind of look at, well, the bottom surface is just this flat plane here. It's the xy plane, which is z equals 0. And then we go up to the plane itself, to kind of that inclined plane leaning kind of backwards into the screen, which is just this equation but solved for z. So it would be 1 minus x minus y that we're looking for there. Now to find the bounds for x and y, remember we're going to actually look at r. So this is q, and then r is only in the xy plane. And we can see it, it's actually that shaded region down there, right? It's just a triangular region from the origin to 1 on both of the axes. So if I say try and make then an equation for y, well, y goes from this bottom line, which is 0, to this inclined line. So for that inclined line, we're going to have to try and find an equation for it. And we can just see that it's a regular line, so we can just look for, well, it has a y-intercept of 1, and then it has a slope of -1. So it's just going to be 1 minus x. So y goes from 0 to 1 minus x. And then we can see that x goes from 0 to 1. So we've got our 3 sets of bounds then for this pyramid type solid. So when we set up our triple integral then, we could go ahead and put the x bounds on the outside, so we go from 0 to 1. Then the y bounds, we go 0 to 1 minus x. And then the z bounds, which went from 0 to 1 minus x minus y, and we're just going to integrate 1, and then following the order of those bounds, it was a dz, dy, dx, matching the bounds from innermost to outermost. Lining up that then to integrate, we can take a look at, Well, the integral of 1 dz is just going to be z, so we're going to have a double integral still. So we had 0 to 1, 0 to 1 minus x. We're going to have z, and z is going to be evaluated from 0 to 1 minus x minus y, and this will be dy dx. And then filling in that, notice we just plug in the 1 minus x minus y. So we're going to have the integral 0 to 1, 0 to 1 minus x, and then we're going to get 1 minus x minus y, and then minus 0 on the inside. So then we're just left with this, dy dx. Now, integrating with respect to y, notice we've got, well, the 1 with respect to y will go to y. Negative x will go to, it's really treated like a constant because we're integrating with respect to y, so it's going to go to negative xy. And then negative y will go to negative y squared over 2. And we're going to plug in 0 and 1 minus x. So then plugging in that, we can see 0 to 1. So plugging in a 1 minus x, we're going to get 1 minus x times 1 minus x minus 1 minus x quantity squared all over 2. And this will be dx. Probably what will be easiest at this point then is to just simplify all of this algebraically before we integrate. So we could do the integral 0 to 1, 1 minus x, minus another x, plus, because it's a negative x times a negative x, so plus x squared. And then we'll have, let's see, 1 minus x quantity squared is going to be 1 minus 2x plus x squared. So we'll really have minus 1 plus 2x minus x squared, but those are all over 2. So perhaps then we might even distribute that over 2. So we might just go ahead and write, instead of a negative 1, it's a minus 1/2. Instead of a plus 2x, it's just plus x. And then it's minus an x squared over 2. So just distributing that 1/2 to each of those parts. Okay. Now we got to combine some stuff. So 0 to 1, let's see, we have 1 minus 1/2 will be 1/2. Negative x, we've got negative x minus x plus x, so minus x is what's left there. And then we've got x squared minus x squared over 2 will be plus x squared over 2. So then integrating, we're going to have a 1/2 x minus x squared over 2, and then plus, we're going to go up to x cubed, divide by that new power of 3, which gets multiplied by the 2, so we're really over 6. And we're going to evaluate this from 0 to 1. So plugging in 1, we get a 1/2 minus a 1/2 and plus a 1/6. Plugging in 0, we just get 0. So then after all the cancellations, we're just left with 1/6. And if we had units, that would be units cubed because it is a volume. So that's that volume of that kind of pyramid-shaped region, that solid that we had up above.